Hey you guys, welcome back to the Calculus Fun Room. In this video, I want to discuss with you what we might call derivative rules or derivative shortcuts. Now in the prior video for section 2.8, what we had done was we said for some function f of x, its derivative was given by, and we had a limit definition. You sometimes call this the difference quotient. And we were looking at the limit of f of x as x approaches 0. So f of x plus h minus f of x as h approaches 0. And again, real quick visual representation. If we were looking at x and we moved some distance away, we had 2 points on the graph. We talked about the slope of the secant line between those 2 points. And then as h goes to 0, right, this point slides towards this point. When we do that process, we end up with the tangent line. So we had that visualization. That was our concept. Now in that video, we would use this limit definition to calculate the derivative of a function in a symbolic form. So one of the examples we did f of x equals x squared, and we got the formula 2x as the derivative. So in the next sequence of videos, what we want to look at is not having to do this lengthy limit process. So the reason we discussed this process in the prior videos was so conceptually we had a deeper understanding of what a derivative does for me, right? It measures a rate of change. And we had some ways in which we applied that idea of rate of change, one of them being the slope of a tangent line. The other one being we were taking an average rate of change, making it become instantaneous. Right? The applications we typically looked at there were like an average velocity and instantaneous velocity. So we went through this whole limit process, this visualization, so we could focus on those concepts. And what we want to do is get a little bit more efficient here. Instead of having to use that limit definition, we want to have some shortcut rules. So in this video, we're going to discuss kind of what I would call the first group of shortcut rules, and then the next video, we'll discuss some additional rules as well. Now, again, I like to keep videos relatively short. I don't really want to spend more than 30 minutes here. So I'm not going to do any deep, lengthy, rigorous mathematical proofs or derivations. Every textbook, the textbook that you're using is going to provide those proofs, those derivations. I want to stay focused really on how we're going to apply those concepts, right? and look at word problems, excuse me, and applications of the work that we're doing. So the first thing I want to talk about is in a prior section, most likely you did some derivatives, and let's suppose the function we looked at was x squared. You would have used that definition and found that its derivative was 2x. Right? These are usually exercises within a homework set. If you had f of x equals x cubed, you would have used that limit definition and found f prime to be 3x squared. And sometimes you'll even take the next step. You'll look at x to the fourth, and you'll see that f prime is 4x cubed. So what we end up noticing is a pattern here. Right? In other words, if we have f of x equals x to some power, what we see in this pattern is basically the exponent we're pulling in front as a coefficient, and then the exponent we subtract 1 and it becomes 3 in this example. All right, so the general rule is I'm going to take the power, I'm going to pull it in front as a coefficient, and then the exponent for the derivative is 1 less from the original function. So what we typically see presented as the power rule looks something like this. And if we have x to the n, we're going to bring the power in front as a coefficient, and then we're going to subtract 1 from the exponent, and that's the exponent in the derivative. Now usually in a conversation in a calculus textbook, at this point you discuss n being a positive integer. So usually in the homework set, you're looking at problems or equations like x squared, x cubed, x to the fourth, and these exponents are positive integers. We could call those natural numbers. So n is 1, 2, 3, 4. And this rule we're officially, I should say initially, generalizing that this is true only for positive integers. But the reality is it's true for all real numbers. Right, and what I mean by that, like usually in a prior section, I think we might have done this in our prior video, if we look at something like f of x equals the square root of x, we would use that limit definition to evaluate that derivative. And what we would end up noticing is that we get f prime is 1/2, or I should say 1 over 2 root x. That was what we would ultimately get out of that limit definition. And that was a lengthy process, but that would ultimately be what I get out of that rule. Now we can use the power rule to do this. Right? We can write the square root as a 1/2 exponent. And then if we apply our power rule, we're going to take that exponent, pull it in front as a coefficient, and then we're going to subtract 1 from our exponent. So we're going to take 1/2 subtract 1, and that's our derivative. So f prime, so remember, this is going to be 1/2 x to the negative 1/2 when I subtract those exponents. And then this is really 1 over. Right, so we take the reciprocal. Properties of exponents says we can take the reciprocal of the base and it changes the sign of the exponent. So in this particular example, we end up with 1 over 2 root x. So again, usually in a very rigorous conversation, you discuss the power rule being true for positive integers, and then you look back at using the definition to evaluate the derivative on a radical, and then you generalize further. You come back to this power rule and you say, well, it's true for all rational numbers. So if my exponent is a rational number, then I can also use the power rule to take its derivative. And then furthermore, you can take one more step back and ultimately say that this power rule is true for all real numbers. For exponents that are real numbers, right? So for f of x equals x to the n, where n is any real number, f prime is n times x to the n minus 1. So it's true for integers, it's true for rational numbers, and it is true for real numbers. So again, in general, you might see the power rule represented in this type of manner. For f of x equals x to the n, f prime of x will equal n x to the n minus 1, and n can be any real number. All right, now in some textbooks, they will look at two specific applications, or two specific cases, I should say, of this power rule. One of them being what we might call a constant rule, but I don't like to call it the constant rule. So what this says, right, this expression says I'm going to take the derivative of a constant. If I take the derivative of a constant, that is going to be 0. And so if we have the power rule here, right, let's say the second rule would be the derivative of a constant is 0. And the easiest way to justify this is to think of a graphical representation. So if I graph the equation y equals c, y equals a constant is a horizontal line. And remember, the derivative of any function is the slope of the tangent. So the slope of the constant function, the slope of this horizontal line is 0. So we can see there's the rate of change of the constant function. It has a slope that is 0. And then sometimes another subcase is that the derivative of the linear function y equals x is going to be 1. And again, another visual interpretation to that is if I graph the line y equals x, you know what I meant to do over here was call this y equals a constant. So here's the line y equals x, and again the derivative of that function is saying what are the slopes of the tangents. And if I look at this graph, the slope is the same everywhere, and it's a slope of 1, right? If we think of mx plus b, Right? My slope is 1 here, and there's the derivative of x. It is just 1. Now, the reality is these are just special cases of the power rule. Right? So, for example, if we think of y equals a constant, keep in mind we can actually write that as a constant times x to the 0, right? Because anything to the 0 is 1, right? So if I use the power rule on this in particular, right, I'm going to bring the power down and then times x to the 0 minus 1. So x to the negative 1. So I have c times 0, x to the negative 1. And 0 times anything is 0. So this rule that is sometimes separated, presented as a separate rule, is really just one case of the power rule. And then ditto for this guy here, right? I mean, y equals x is really x to the 1 power. And then if I use the power rule there, I'm going to take the 1, bring it in front, and then I'm going to have x to the 1 minus 1, which is 1 times x to the 0. Anything to the 0 is 1. So we can see the rule that we're getting up there. Again, derivative of x is 1. So we can justify each of those subcases graphically, and we can justify them with the power rule. So we've talked about 3 cases, right? 3 shortcuts, if you will, 3 rules of derivatives, and they're all really the power rule. We looked at a couple of examples. We looked at the derivative of x squared being 2x, derivative of x cubed being 3x squared. We even looked at the derivative of y equals root x. So let's go ahead then and take a look at a couple other examples. So in this example, what I want to do is let's say for f of x equals, oh, you know what? Hang on a second. Before I do that, there's one other rule that I do want to talk about with you. I apologize. So one other rule that I want to talk about, and this is what most books call the constant rule. So what the constant rule says is if I'm going to take the derivative of a constant times a function, that I can really pull the constant out and differentiate the function itself. So this is like an order of operations is what it really is. Okay? So and again, we could do a formal, rigorous proof of this. I'm going to forego that for the sake of not having too lengthy of a video. By all means, take a look at any textbook. You'll see a proof of that rule. You know, an example of that rule might be something like y equals 3 times x to the 5th. So if I'm finding y prime, I'm finding the derivative. Right? What I'm in essence going to do is pull the constant out, and I'm going to take the derivative of x to the 5th. So I'm going to go ahead and use the power rule here. Derivative of x to the 5th is bring the power down and then take 1 away from the power. So we end up with 3 times 15, excuse me, 3 times 5 is 15, and then we'd have x to the 4. So here's y prime for that particular example. All right, I was getting a little excited about doing derivatives, and I left out the constant rule. Right? So if we have the derivative of a constant times a function, we can in essence pull that constant outside the derivative operator. So here it is outside the derivative operator, and then we take the derivative of the function, and then we multiply the constant back on to its derivative. So again, our example is we pull the 3 out front, then we take the derivative of the function, and then we multiply the 3 back into the derivative. Right? So the derivative of a constant times a function is a constant times the derivative of the function. All right, now that we discussed that, let's take a look at a couple other examples here. And one of the goals of these next examples that I want to do with you is to mix in different notations. Right? So, as I was going to say, let's say for the function, let's say, what do I want to do here? Let's say 5 times the square root of x, right? Find f prime. All right, so in this example, one of the things that I want to remind ourselves of is notation. So if I have a function f of x, we can communicate that I want the derivative by using f prime. So if I use the prime notation, that indicates that I want to take the derivative of the function f. And again, remember, historically, Isaac Newton, Gottfried Leibniz, ultimately were both said that they were the fathers of calculus. Now, initially, Leibniz and Newton, they lived during the same time frame. And they were actually developing this concept of calculus independently. And Newton actually ended up not publishing his papers until he was pretty old, right before he died. Leibniz had published his papers first. So initially, Leibniz was called the father of calculus, but later on, Newton and Leibniz had really been developing these conversations at the same time. So they both were really the fathers of calculus. Now, Newton used prime notation. And so this is actually a nice shorthand way to communicate that I want a derivative. I can do f prime. And it doesn't matter what the name of my function is. If this is g of x, I'm going to write g prime. If this is h of x, I'm going to write h prime. So that prime notation indicates a derivative. Now, for this particular example, I'm going to use the constant rule and the power rule. So the first thing I'm going to do, as we talked about before, I'm going to write the radical as a rational exponent. Uh-oh. That is not the derivative. My apologies. This is just the same function that I have rewritten algebraically. So this is my function. Now we're going to take the derivative. So I'm going to pull the constant out. I'm going to take the derivative of the function. So I'm going to bring the 1/2 in front. Right? I'm going to take the exponent, pull it in front as a coefficient. And then I'm going to do 1/2 minus 1 as my exponent. We really already did this, right? We talked about how this was x to the negative 1/2, and that's a root x in the denominator. So I'm going to have 5 over 2 root x when I simplify. So here's my derivative of 5 times root x, and it becomes 5 over 2 root x. Let's look at another example. So in this example, I want to introduce our other notation, remind ourselves of prior video what our other notation was. So let's suppose, let's say for, let me say y equals, let me say pi r squared. Let's find dy dr. So this is the Leibniz notation, right? Leibniz notation doesn't use primes, it uses dy over dr. And the reason that Leibniz used this notation, right, you know, he was talking about slopes of tangents, let's say, right, rates of change, and the slope of a line is delta y over delta x. So he was connecting to this notation, and he was saying, you know, technically this was an average rate of change, and then the instantaneous rate of change, he wrote the delta as a d. So dy over dr is representing the derivative of the y variable with respect to r. And what I like about this notation is it clearly indicates to me the dependent variable, and it clearly indicates to me the independent variable, kind of like we see in this notation here. I prefer this notation, but the prime notation is a little quicker and more efficient. All right, so if I'm finding dy dr, right, the r is the independent variable, so the pi is a constant, and then I'm going to take the derivative of r squared. Now I'm going to stop for a second here because this is another form of notation, and this is the derivative operator. So this says I'm going to take the derivative of this expression. And again, it says I'm going to take the derivative with respect to r of this expression. So I'm treating r as my variable. So just like if this was x squared, I would use the power rule. This is r squared, and I'm going to just treat that as a power rule. Right? So I'm going to bring the power down, take one away, and there's my derivative for pi r squared. Okay. So in these prior two examples, we've used the power rule. We've also used the constant rule, right, where we take our constant and we pull it in front of the derivative operator. We've also discussed the different types of notation, the prime notation, the Leibniz notation, and then the derivative operator notation. I want to do a couple more examples. to just look at a couple different situations here. In fact, actually, I want you to do these for me. Right? So I'm going to write these down on the digital notes, and then I want you to pause the video and attempt these on your own. And then unpause the video and we'll come back and talk about these together. So the first one I want you to find for me is, let's say, find f prime of x for, let's say, f of x equals 5 over x cubed. And then the second one, I want you to find the slope of the tangent to, let's say, y equals x times root x at x equals 1. Now, before you pause the video, I want to give you a little bit of a hint, right? For both of these, when you're doing the derivatives, keep in mind what you need, right? What you want is x to a power. So, before you can take the derivative of either of these functions, you need to simplify them algebraically to get them into x as a power, so that then the derivative rule, right, you can use the power rule. All right, so there's my hint. I want you to stop the video, try these on your own, and then when you're done, unpause, and we'll go over these together. All right, now that you have unpaused the video, welcome back. Let's take a look at these together. Right? So the first one, we had the function 5 over x cubed. And in order for me to use the power rule, 5 over x cubed, in order for me to use the power rule, first I have to simplify this and get it as x to a power. Right? So my hint, right, was to get this as x to a power. We're going to use a property of exponents that we kind of already mentioned when we were doing the radical problem. So when I have a variable, right, to a power, I can take the reciprocal of the base and change the sign of the exponent, right? So I'm taking the x in the denominator, pushing it into the numerator so that it's the reciprocal, and then I have now x to the negative 3. This is example 1. Right? Now I'm going to take the derivative, right? So now I'm going to have f prime. I'm going to pull the constant out front, and I'm going to take the derivative of the function x to the negative 3. So what is the derivative of x to the negative 3? So I'm going to take the exponent and I'm going to pull it in front as a coefficient, and then I'm going to take the exponent of negative 3 and subtract 1, and there's my power rule. So what I end up in this case is negative 15 as my coefficient, and then I get x to the negative 4. Now this is definitely an acceptable expression for the derivative, but because we have a negative exponent, we usually want to simplify that and get rid of the negative exponent. So we're going to push it back into the denominator and make the exponent positive. Right? And so there would be the derivative of 5 over x cubed. All right, let's take a look at the second example that we had. And what the second example asked was, right, to find the derivative of, well, actually it said find the slope of the tangent to that function at x equals 1. And again, my hint was you needed to get this function to be x to a power. So in this case, the way I'm going to algebraically simplify that, right, I'm going to write the radical as a 1/2 exponent. And so when I multiply like bases, I add exponents. So my function is really x to the 3/2. So my function f of x is really x to the 3/2. And now that I have x to a power, I can take the derivative of that function. So I will bring the power down. I will bring the power down. And then I would take 1 away from the power. Now I'm going to write the number 1 in this manner, right? When I subtract 1, the common denominator is 2. Right? So I really have 2 halves. 3/2, right? So I want to match that common denominator. So this is really 3/2 x to the 1/2. Right? So really 3/2 square root of x as my derivative. That's f prime. Now remember, why did I take the derivative here? I was being asked for the slope of the tangent. So the tangents have slopes that come from the derivative, right? The derivative is my rate of change. It is the slope of my tangent line. So this equation, 3/2 times root x, is the slope of every single tangent on this curve. So I want the slope, right? I want the slope at x equals 1. So that's going to come from f prime at x equals 1. So I have 3/2 square root of 1, and that gives me 3/2 as the slope of the tangent to that function at x equals 1. Okay, so a couple other things we would typically see in a section like this would then introduce the idea of what we call the sum or difference rules. So the sum rule would look something like this, right? I would say if I have the sum of two functions and I'm taking their derivative, I'm going to use the lazy prime notation, right? What I can do is take the derivative of each individual function and add those together, right? So this is saying the derivative of the sum is the sum of the individual derivatives. Again, in a calculus textbook, you're going to see a rigorous proof of where this formula comes from. I'm going to skip that for the essence of time. We could also see the Leibnitz notation version. We could have the derivative of the sum, and then we could say that's the sum of the derivatives. So I'd have the sum of the derivative of each individual expression. I'm going to use some really bad terminology here, and I'm going to say that the derivative can distribute over a plus sign, and that is just horrible terminology because the derivative doesn't really distribute, right? It's not a number that multiplies. This is an operator. So this operator can move over addition and subtraction. So I actually could have what we might call the difference rule for derivatives. And it just says the same thing. It says the derivative of a difference is going to be the difference of the individual derivatives. Okay. And that shouldn't be a surprise, right? I mean, if you think about subtracting is the same thing as adding the opposite, right? 5 minus 2 is 5 plus negative 2. So these are intimately connected, right? The sum and difference rule really say the same thing. Now, what this rule provides for us is the ability to take the derivative of, let's call them monomials, right? So if we have expressions that have multiple terms, we can, in essence, move the derivative over addition or subtraction. So as an example, right, let's say we have the function, actually, you know what? Let's do a little bit of a deeper example. Let's say we want to find the equation of the tangent to, let's say I'm going to use some different variables. Let's say h of t equals, I'm just going to make some stuff up here, all right? This might get a little dangerous. I'm going to have 3 times the 4th root of let's say x to the 3rd. Why did I say x? Look at that. See, we all get so ingrained of using x. I'm using t as my independent variable. So 3 times 4th root of t cubed minus, let's say, what do I want to do? Let's say 2 over t plus 4. I want to find the equation of the tangent at, let's make this as easy as possible on ourselves, and let's say at t equals 1. Okay. All right, now, to find the equation of the tangent line, we want to find the equation of a tangent. And in order to find the equation of any line, right, we would need to do, right, the point slope formula. So here's the equation for any line. And then, we need a point, and we need the slope. Right? We did this in prior video, right? But just to remind ourselves where we're headed. So the slope of this tangent line comes from the derivatives of the function. So we need to find the derivative of this function, and then we're going to plug in t equals 1, and that's going to give us the slope of the tangent. All right, so to find the slope, we need to find the derivative. Now, before I find the derivative, I want to simplify this expression, right? Because I'm going to use the power rule, Right? So let me switch the color red. So I'm going to write h, my function h, as, so all right, let's look at properties of exponents here. So the fourth root is really a 1/4 exponent. So I'm going to write this as t cubed to the 1/4 power. And then t to the 1 in the denominator is really t to the -1 in the numerator. Now, before I take the derivative, I'm going to clean this up a little bit more. So when I have an exponent raised to an exponent, I multiply those exponents. So what I'm really differentiating is t to the 3/4 when I multiply those exponents. All right, now let's take the derivative. So now I'm going to find h prime. I'm going to use the power rule every time. And I'm going to pull the constant out every time when I do that as well. So I'm going to pull, I'm pointing to the wrong place. I'm going to pull the constant out. And I'm going to take the derivative of t to the 3/4. So I'm going to bring the power down, and I'm going to take 1 away. And again, it's instead of subtracting 1, I'm going to get the common denominator of 4/4 just to make my subtraction a little easier. Then I'm going to pull the constant out of -2. I'm going to take the exponent down. I'm going to take 1 away. And then remember, the derivative of a constant is 0. So let me clean that up a little bit more. So what I end up with is my derivative as 3 times 3, which is 9/4. And I'm going to have t to, what's this? 3 minus 4 is -1. And then I have -2 times -1 is +2. T to the -2, and then no need to rewrite the 0. And then so this is a -1/4. I'm going to push it into the denominator and make it a +1/4. And then I'm going to push the t to the -2 into the denominator as well. Make it 2/t². And then go ahead and I guess I'll write the 1/4 as a fourth root. So I got the fourth root of t, and then plus 2/t². All right, so there is our derivative. Remember, the derivative gives us the slope to every tangent line. We want the slope at t equals 1. So my slope of my tangent line is my derivative evaluated at t equals 1. So if I plug 1 into here, fourth root of 1 is 1. 1 squared is 1. So I'm going to have 9/4 plus 2. And I'll go ahead and get a common denominator of 4. So this is 2/1. I'm going to multiply by 4 in the denominator, multiply by 4 in the numerator, and I get a slope of 17/4. So I have my slope of 17/4. I need my point x1, y1. Right? So what's the point x1, y1? Now, technically, I'm using the wrong symbolism here, right? This is really the domain t1. The y values were h's. Whatever. Same thing conceptually, right? We have an input of 1. What's the output? And I need to scroll up just a hair here. So here's my original equation. Right? Actually, let me scroll a little further. So I need the y value on the original equation. So I'm going to plug t equals 1 into my original equation so I can get the y value on the graph. So I have, this is going to be 1 cubed. Fourth root of that is 1. So I have 3 times 1 minus 2 plus 4. So I have 3 times 1 minus 2 plus 4. Right? This is h of 1. Right? So that is 3 times 1 minus 2 plus 4. Which is, what's that? 3 minus 2 is 1, plus 4 is 5. Okay? So if we're finding the equation of our line, y minus y1 equals m times x minus x1, right? We have y minus, my y value there was 5. My slope was 17/4, and then my x value was 1. Again, this is really not the correct symbolism. Right, my y values were h's, and my x values were t's. Usually when we're being asked to find the equation of a tangent line, what we're going to do, is solve for y and get y equals mx plus b. So I could go through the algebra here of solving for h so that I get the form mx plus b. And if I do that, what I would get, have 17 fourths x plus 3/4. So there's the equation of our tangent line to the function given at t equals 1. Now, one thing I want to discuss here is technology. So let's say we're going to use some technology to check our work. Now, for this particular example, what I want to do to check is I want to graph my original equation that we have here at the very top. So here's my original function, and then I'm going to graph the equation of the tangent that we just got. And I want to see that the equation and the tangent line are actually tangent to each other. So if I'm using, Texas Instruments type of calculator, I'm going to bring up my calculator, hit the y equals key, and I'm going to graph my original function, and I'm going to graph the equation of my tangent. I'm going to pause the video and type those in real quick. All right, so I have typed everything in. Instead of having to do the roots, I did the 3/4 power. Right? So we had 3 times x to the 3/4. Let me pull this down. 3 times x to the 3/4, right, minus 2 over x. I just went ahead and did that division here, 2 over x, and then plus 4. And then here's the equation of my tangent line. So I did a zoom 6 graph here, and we can see in blue the original function, and then in red the tangent line, and we can see that it looks like a glancing blow, right, at the point where x equals 1 there. Now keep in mind, I could also use a website like Desmos.com. So if I go to Desmos.com and I graph, so what I want to do is type in each of those equations. So let me pause and type those in. All right, so I have typed those in. Here's my original function. Here's my tangent, and I can see at that point they're tangent to each other. I can see the tangent line come in and do a glancing blow at that point. So that's a nice check visually of the tangent to the original function. Now, one other thing I want to talk to you about, and so we can end this video and finish off this section. All right, so the last topic we would see in a section of this nature would be the derivative of an exponential function. Now, what I do want to do is take a step back for a second and let's explore where this derivative comes from, because it's actually really cool, and it connects back to our concept from the prior chapter. So let's suppose that what we want to figure out is for the function that is exponential in form, right? What's f prime? What's the derivative of that function? Right? So this is a generic base b. This could be any base we want it to be. This could be 2 to the x, this could be 3 to the x, this could be 5 to the x, this could be 1/2 to the power of x. This could even be the base e exponential, e to the x. So we're letting the base be arbitrary. And keep in mind, initially, from our prior chapter, the definition of the derivative gives us a way to calculate the slope of every tangent, right? The slope of the tangent line, our instantaneous rate of change. Now for this particular example, I'm going to take x plus h, I'm going to plug it into the domain. Uh-oh, I'm forgetting my limit symbol. So I have the limit as h goes to 0. So I have b to the x plus h minus b to the x all over h as h goes to 0. Now back in that prior chapter, when we would write this expression, we could evaluate this limit typically in one of two ways. So if we had like the function x squared, what we would do when we plug in x plus h is we'd have x plus h squared, and we're able to FOIL that out, right? Multiply that out and do some cleanup. We also looked in the prior chapter, my function was square root of x, so I'd have square root of x plus h in this limit, and then we could use like a conjugate trick, multiply top and bottom by the conjugate, and that would help us evaluate this limit. We don't have any algebraic trick we can really do to fully evaluate this limit. And what I can do to make this a little bit simpler I'm going to split up this exponential term, and I'm going to write that as b to the x times b to the h. Right, so remember, the reason that that's legal is when I multiply like bases, I add exponents. Right? So when I multiply these like bases, I add these exponents. And I'm just going backwards. I'm splitting that up. And so the reason I'm going to do this is I can now factor out the b to the x term, and I get b to the h minus 1 all over h. The limit is h goes to 0. Now, in terms of this limit process, the limit is only evaluating the h expression. So the b to the x has nothing to do with the h variable here. So I'm going to actually pull that out of the limit process. B to the x, and then we have times the limit of b to the h minus 1 all over h as h goes to 0. So the question then at this point is, what does this limit equal? Right? What does this guy equal? So first of all, again, we can't evaluate that limit using any algebraic techniques, at least not anything we've talked about up to this point. So a couple things to think about, right? First of all, does this limit exist? That's the first question, right? So we have a limit. Does the limit exist? Now, assuming that the limit does exist, then this is equal to some finite number. Right? Usually we say a limit equals some number L, right? So I'm going to say that this equals L times e to the x. Okay? So assuming this limit exists, which it most likely does, that limit would be L. Now, if we stop for a second and we think visually, does this limit exist? Remember, what we're doing is we're finding the derivative. We're finding the derivative of an exponential function. And remember, an exponential function usually looks something like this, at least as long as the base is bigger than 1. If the base is less than 1, it decreases. So in either of these scenarios, the graphs are smooth and continuous. So there's no corners where the derivative would be undefined. There's no asymptotes, vertical asymptotes, or holes in the graph where the derivative would be undefined. So the derivative is undefined at every point on this graph. So this limit will exist. It'll be some finite number. Now, what we can do is we can explore this expression here. So I want to take a moment and let's explore that expression. And what I mean by that is I want to pick a couple specific values of b. So let's come down here, I'm going to switch back to green, and let's suppose we pick b equals 2. Right? So for example, we're looking at y equals 2 to the x. And what I want to look at in this case is if b is 2, if I'm looking at 2 to the x as my function, and b is 2, I have 2 to the h minus 1 all over h. So 2 to the h minus 1. 2 to the h minus 1 all over h, and I'm letting h go to 0. How close to 0 do I need to get? Enough to see a pattern here. So I'm looking at this expression when the base is 2. I'm going to come back and fill that in a moment. Then let's suppose the base was 3. So let's explore two different bases, right? So again, I'm looking at y equals 3 to the x. So the derivative of 3 to the x is going to be 3 to the x times whatever this limit is. So I'm going to explore what that limit is when the base is 3. So h is going to go to 0, and we're going to look at what that limit does as the base is 3, right? And as h goes to 0. All right, so I'm going to have to take out my calculator and type this in to my to figure out that limit. Right? So here's how I'm going to do that. Let me clear out what I did here. So what I'm going to do is go to my expression. Now what am I looking at? I'm looking at 2 to the h minus 1 all over h. Now my calculator, I'm going to use 2 to the x. So I'm going to say 2 to the power of x minus 1. And then I'm going to divide all of that by x. So this is the same expression, right? This is 2 to the h minus 1 all over h. And I want to let h go to 0. So to be efficient, right, we talked about this in a couple videos prior when we did limits, right? The efficient way I like to do this is go to the table. But first I'm going to do table set, and I'm going to change the independent variable to be ask. And now when I go to the table, I do second graph. I can plug in values for h. So I can do 0.1, 0.01, 0.001, and 0.0001. So here's my table of values, enter. Here's my table of values that I would have. Let me pull this to the side for this table. So let me just copy and paste this for a moment. Let me pause. All right, so there's the copy and paste of my table. And now I want to look at this other expression, right? So I'm going to look at 3 to the h minus 1 all over h when we were looking at the 3 to the x function here. Right? So let me pull my calculator back up. And what I want is 3 to the h minus 1. So let me go back to my y screen, and I'm going to change this to 3 to the h minus 1 all over h. And when I go back to my table, I had already plugged in those h values. So here's what that expression is approaching. All right, so here's those limiting values. Now I want to let me zoom out for a moment here because I want to summarize what we've just discussed. I hope you can still see this as I zoom. So what we started off discussing is saying, what is the derivative of an exponential function? What's the derivative of y equals b to the x? So we used the limit definition, we plugged in, we did some simplification, and we found out that the derivative of b to the x is going to be some number times b to the x. That should be b to the x. See what happens? I start having so much fun with calculus that I can't even write anymore. Right? This is a b to the x, which is what I wrote here. So we do some algebra simplification. We find out the derivative of b to the x is b to the x times some number. So we said, well, what would this look like if the base is 2? Or what would this look like if the base is 3? So if we looked at 2 to the x, here's what that base expression became. So in other words, our number when we have 2 to the x is 0.6932. So let me write that down as our summary, right? So if we have y equals 2 to the x, y prime is approximately 0.6932 times 2 to the x. That's what that table showed us. And then again, this one for y equals 3 to the x, right? This says that y prime would approximately be 1.0987 times 3 to the x. Okay. All right, so, when we looked at this limit a moment ago, we kind of asked ourselves, right, does this limit exist? We looked at the graph of the exponential, and we said, well, sure, that limit should exist because the exponential is smooth and continuous. So this limit should be some number L, and we found the number L for 2 specific cases. So if base is 2, we found that number L. If base is 3, we found that number L. Now, what we're going to do in this particular section, we're not going to look at the derivative for every possible base. We're not going to write a formula. We're not going to have a shortcut for every possible base. We're going to do that in a couple sections after we discuss logarithms. What we are going to do in this section is look specifically at e to the x, right? However, the reason we had this conversation was to discuss that the derivative of an exponential is the number times that exponential, some number times that exponential. Derivative 2 to the x is some number times 2 to the x. The derivative of 3 to the x, man, I have so many typos here. The derivative of 3 to the x is going to be y prime equals some number times 3 to the x. So what's the derivative of e to the x? That's really our last question in this section. So I want to point out to you here real quick how this conversation usually goes in a textbook. Right? We have the derivative being some number times b to the x. So the question really is, what base will provide this as being the number 1? That's usually how we frame this conversation. Right? So what base has the limit equal to L, that's 1. So we want this limit to be 1. So here's our rationale. We see that a base of 2 gives a limit that's less than 1. We see that a base of 3 gives a limit that's greater than 1. 1. So our base must be between 2 and 3. And I don't want an equal sign there. It definitely doesn't equal 2. That's about 0.69. So our base has to be somewhere between 2 and 3 for this limit to be 1. Now, what is that base? Is it 2.5? Is it 2.6? Is it 2.7? All right, so at this point, this gives us the opportunity to define the base e. So basically how we typically define the base of e in a calculus course is we say e, right, is the number such that that limit that we had, right, of e to the h minus 1 all over h equals 1. Right? So we wanted that coefficient to be 1. We wanted this coefficient to be 1. The only way that that's going to occur is a base of e. Now remember that in an algebra class or even on a calculator, right, e is approximately 2.718 roughly. So if I come back to this formula here and I plug in e, I should see that limit be 1. And 2.718 satisfies the base being between 2 and 3, as we just discussed. So I'm going to pull up my calculator real quick. And I went ahead and typed in e to the h minus 1 over h. And when I go to my table, I can see that limit approaching 1. And so again, in a calculus class, that's typically how we define the base e exponential. All right, so now that we've talked about the base e exponential, right, in summary, what we're discussing here, what all of that exploration was about, is that the derivative of e to the x is 1 times e to the x. Right? So that limit that we just explored for about 10 minutes is going to be 1 when the base is e. So the derivative of e to the x is e to the x. And this is the last thing we look at in this section. So I want to do one more example where we put all of this together with the power rule, the sum rule, the difference rule, and now the derivative of an exponential. All right, now hold on to your hats because I'm going to do some wicked fun stuff here just to hammer home some of the concepts that we've talked about here. So in this example, I would just want to say something like for the following function, right? For f of x equals, let's say 3 times the times x to the 1.5. Minus, let's say, 2 times x to the pi plus 5e to the x. All right, so getting a little crazy here. All right. This is getting exciting. All right, now actually, I'm going to challenge you. I'm going to ask you to pause the video and try this problem on your own. See if you can get the answer that we're going to get in just a moment. So go ahead and pause, and when you're done, unpause. Okay, now that you've unpaused the video, let's take a look at what the result would be here. So I'm going to stop, writing all of the steps, all right? And I am going to kind of say the step and then write the result. So when I look at the derivative of a sum or a difference, right, I'm going to, in essence, move the derivative over the subtraction and addition sign. And I'm going to differentiate this term, and then I'm going to differentiate this term, and I'm going to differentiate this term. So I'm going to differentiate each of those monomials separately, knowing that this derivative, right, of a difference is the difference of the derivatives, and derivative of a sum is the sum of the derivatives, so on and so forth. So when I differentiate this first term, I'm going to pull the 3 off, and then I'm going to differentiate x to the 1.5. I don't think I gave myself enough room there. So I'm going to bring the power down, and then I'm going to subtract 1. 1.5 minus 1 would be 0.5. And then I'm going to pull the constant out. I'm going to take x to the pi. I'm going to bring the power down and then subtract 1. And then I'm running out of room on my digital paper. So this last term, I'm going to bring the constant 5 out. And what is the derivative of e to the x? We just said that that is e to the x. So there is my derivative. So let's say f prime of x. All right, so f prime of x would be, let's see, 3 times 1.5. It's going to be 4.5 x to the 0.5. All right? And then this is just minus 2 pi. And there's really nothing, excuse me, that is an x. There's really nothing we can do. I mean, we could get a decimal for that, but I'm going to leave it as x to the pi minus 1. Obviously, this would be 3.14 minus 1, which is 2.14. And then 5 times e to the x. So they would be my derivative in that case. In summary, we've talked about a couple different derivative rules, right? So let's just summarize. Right? We talked about the power rule, and we said that the derivative of a power is that we would, in essence, bring the power down, take 1 away. We talked about the derivative of a constant being 0. We talked about the derivative of x being just 1. You know, in general, the derivative of any linear, right, is m. Then we talked about the sum and difference rule. So we talked about the sum or difference. Right? I'm going to get lazy here, and I'm going to get even lazier and jump to prime notation. So the derivative of a sum is the sum of the derivatives, and then, let me come back up here. The derivative of the specific exponential e to the x is just e to the x. In the next video, what we're going to do is take a look at a couple other rules of derivatives that we call the quotient rule and product rule. But for now, this ends this conversation.